started. So this is the ethics part of the week. So of course we would hope that the whole week was also ethical. And so now we have two speakers, and these two speakers will also be on the panel. We'll have two additional panelists join us. So the first one is Sharad Goel, who's worked on many things, but today he'll be telling us about fairness and bias.
Hi. Thanks for the introduction and for the invitation to speak. So as Bintu said, I'll talk a little bit about this intersection of fairness and machine learning. And my upfront kind of disclaimer is that this isn't going to be super about deep learning, but I think the ideas are general to any of these types of statistical models. And so I'll try to draw those connections out. So I'm going to make a somewhat controversial claim, and so I want to put it up front first, and then I'll dive into this a little bit more during the rest of the talk. And so my claim is actually twofold. So the first claim is that recently there's been this whole set of definitions to audit models and to understand what it means for these machine learning models to be fair. And I'm going to argue that essentially all of these, or at least a big class of these group-based definitions of fairness, are poor proxies for detecting discrimination. So even though we use these to audit models, I'll argue that they're quite poor at that task. And the second one is even sort of more consequential, that not only are they poor at auditing, but if we were to use these as positive measures to build models, as design principles, then in fact they can lead to these perverse decisions. And so these rubrics that we've been developing over the last several years, they have these twin problems. They're both bad at auditing and they're bad as design principles. So these are controversial, I know. So I'll try to explain this in much more detail, and please feel free to push back as I'm talking, I'll try to explain. Okay, so first I just want to give an overview of algorithmic decision making in a broad, abstract sense. And I'll frame everything in this case study, Machine Bias. Probably many of you have seen this, that came out a few years ago now. It was talking about the deployment of an algorithm to help judges decide whom to release when they're pending trial. So just to make sure we're all on the same page, what is this context? So in the US, after someone's arrested, usually 24 to 48 hours after someone's arrested, a judge has to make this high-stakes decision about whether or not that individual should be released or detained pending this trial, which might happen in weeks or months in the future. And this is tricky. There's this goal is to balance the social financial costs of incarceration. So someone might lose their job, they're disconnected from their family, the state has to pay for incarceration. This is a pretty big social and financial cost to incarceration. And on the flip side, there's this obligation or desire to keep the public safe. And so how does one balance these costs? So historically, how is this done? Judges would use their intuition, their experience, and just base the decisions on that type of information. And just for a little bit more context, these are usually pretty quick. They're like 2-3 minute hearings, and really kind of my caricatured portrayal of this is that a judge looks deep into someone's eyes and says, are you the kind of person that's going to re-offend if I release? Now that's again a little bit of a stretch, but just to give you a sense. Well, so this is again one of the questions. What are they actually using, and are these discriminatory? Okay, so because of, even though experience and intuition, we use this in all sorts of different disciplines, but there's recently been a push to adopt algorithms. I'll say algorithms in quotes here, because really these are just checklists like this. And so here we have a bunch of different risk factors. We have points assigned to each of these things. And so let's take our hypothetical defendant with 2 prior convictions, 2 prior failures to appear, and no prior failures to appear in the last 2 years, and no prior failures to appear before that. This is a real risk assessment tool that is deployed across the country. And we just add up points for all of these people. And now we see this person scored a 5 out of 7, and we might call that high risk. Now again, this is in some sense the exact opposite of deep learning. This is, it's for good reason here that we want something interpretable, we want something simple, we want something that in fact doesn't even require a computer to implement. And I won't talk about it here, but what we actually find is that these very simple interpretable rules, at least in this context, are competitive with state-of-the-art machine learning methods, nonlinear machine learning methods. And so that's just kind of an aside, but this isn't a crazy thing to do. Really what are they doing? They're just running logistic regression in the back with maybe 20 features. They're doing some sort of selection, and now they're generating a rule like this. And they don't seem to be terrible at predictive performance in this context at least. Okay, so now this is just background. So now I want to make two formal assumptions that I'll stick to for most of this talk, and then I'm going to come back to this at the end. So the first big assumption is that these are all prediction problems, and so we need some label. And I'm going to make the assumption that we know that true label. So in the criminal justice context, we're trying to predict whether or not someone will recidivate if released. And I'm going to assume that we know the why. So what does that mean? That really embeds two separate conditions. The first is that we observe exactly what that person is doing at all times, or at least in this narrow case of if they went out and committed a crime, we actually know it. Again, kind of foreshadowing what I'm going to talk about later, is we don't know that in general because we only have these proxies of, for example, whether they were arrested. So we know whether someone's arrested, but not actually whether they committed the crime. So for now, I'm going to assume we know exactly what that label is, whether they committed the crime, not just whether they're arrested. And the second thing that's embedded in this assumption is that we really know the counterfactual. We know what would have happened had they been released. In the historical data that we're training on, we don't know that. We only know what happened conditional on the judge's action. And so all of this counterfactual estimation, I'm rolling it into this y, which you can think of as a potential outcome. So there is definitely, you can't just like give me the y's and I can fit these things, but I'm going to assume right now that we know everything perfectly. So this is a big assumption. I'm going to come back to this. The second assumption, I'm going to argue, is not actually that big. And so what does this mean? That the second assumption is that we can compute this risk perfectly. And this doesn't mean that we're an oracle. It doesn't mean that we know for sure whether or not someone is going to reoffend. What it means is that we don't have any estimation error. So very specifically, if you give me a set of covariates x, and this is just defined, that this might be someone's age, someone's criminal history, all of this stuff, that I can compute this thing exactly, the probability that they would reoffend if released, conditional on those covariates. So again, this is an assumption. It's like a moderately big assumption in the sense that if I need lots of data, and if I'm a frequentist, I can cut up the world into all of these little bins. Let's assume everything is discrete, and now I'm going to look in each of these bins and see what happened with that y. Then I can estimate this. In the real world, I have to do some regularization. I'm going to assume linearity or some other functional form, and I'm going to fit this model. And so there's something wrapped in here, but I would say for the most part, when we have lots of data and we don't have this covariate dimension is not super high, then we can do this reasonably well. So it's still a big assumption, or still an assumption, but I would say it's not nearly as big as this first assumption, which I'm going to come back to.
Okay.
Yeah, please.
So X is not the actual individual, it's a feature representation of the individual.
Exactly. And so this is, it's a good question. It's a little bit, there's like semantic slippage here. So typically you just think of the individual as their covariate vector. I mean, every individual is kind of distinct. And so in that sense, what does this even mean if I'm talking about an individual? But to the extent that we have statistical analysis, we're collapsing that essence of that individual, or whatever we want to call it, to available covariates. But I'm going to use the terminology this individual's risk, even though I'm saying what that statement really means is based on this covariate vector x that I have access to. So there is no sense of true risk anywhere other than this definition, which is contingent on x. And that's what I'm going to talk about more in a minute.
And the vector is discrete, so in every cell you have enough individuals to do some statistics in the cell.
Yeah, so that would say how why is this even plausible? But in general, I can just write this down, right? It doesn't have to be discrete. It doesn't, I don't have to have lots of data. I'm just saying I can estimate this thing perfectly, but of course in practice, the only way I can do this is if I have lots of data, right?
Yes. So again, just to make sure that I understand, it means that you know the base optimal predictor.
Mm-hmm. Yeah.
So there is no learning problem here.
Exactly. I'm taking for this kind of high-level discussion right now, I'm assume that there's no estimation error, that I know everything exactly. And a lot of the assumptions are going into this first. Okay. So now, what does this mean to go from features here, my x's, like age, criminal history, et cetera, to a decision at the end whether or not to detain someone? And this, for simplicity, I'll assume is binary. Well, what that means is that first, often, again, this is a stylized pipeline, but I think it's a useful depiction, is that I'll assume that first you make the prediction, the risk estimation. Then you take that risk estimation and you make some decision based on that. And your decision is going to be based on the risk, and it's also going to be based on the features. So the way I've drawn this is redundant. It doesn't really matter if I have that box. The decision is based on the features. Okay, that's just like a tautology there. But the reason I wrote it this way is to highlight the fact that the prediction should play an important role in the ultimate decision process. Okay, so now let's look at each of these boxes in turn. First, let's look at the prediction box. So the prediction, by assumption, we know exactly, we're just assuming that we have this risk exactly conditional on the features x. So if you give me the x, and it is going to depend a lot on the features x, but if you give me the x, then I know this risk exactly. So that's the prediction box. Okay? So let's think a little bit about what the structure of that prediction is. So here, as I change x, so now this is really the key slide of the talk. Once we understand this object, everything else is pretty straightforward. So I have my risk. I've set my covariates x. And now I can ask for every individual in the population, what is their risk? And I'm going to get a distribution of risk across my population. So the heterogeneity here is not from estimation error. It's coming from differences in the population. So some people might be older, not have much criminal history. They might be on this side. Some people might be younger, have a lot of criminal history. They might be on this side. So I have this variation across the population, but there's no estimation here in this picture. So if x is let's say x is non-informative, so x basically doesn't give me anything that I can use for this risk estimation, what is this distribution going to look like? It's going to look like a point mass right at the mean. So it's going to be very low variance right at the mean. And why is that? Because I can't distinguish between anybody. So if x is just something that has nothing to do with individuals, and I say, well, what is your probability of reoffending conditional on these covariates that you gave me that happen to not be informative? Well, all I can do is guess the base rate. So it's just going to be point mass right at the mean. Now, if x is super informative, what is this going to look like? Well, it'll be concentrated at 0 and 1. So it'll have high variance, and it's going to look like this. Okay, so non-informative x, tight around the mean. Informative x, high variance, bimodal around 0 and 1. Okay, I'll just pause for a minute and make sure we're all on the same page. This is kind of deceptively simple, this kind of picture, but once we understand the mechanics of this, it has big implications for our understanding of variance. Questions? Okay. Great. So now we have to go from our prediction to our decision, which is a binary. And how do we do this? Well, one common way, not the only way, but one common way to do this, to make this type of binary decision, is simply to threshold our risk. So it doesn't matter what those features are. At that point, we're just saying you gave me the risk. The decision is not going to depend on the features anymore. It's just going to depend on the risk. And what am I going to do? I'm just going to draw this line somewhere on my risk distribution, say everyone to the right of this line is detained, everyone to the left of this line is released. Yeah, this isn't the only way to make a decision, but it's both a common one and I would say it's not, at least not a crazy way to make these types of decisions at the end.
I mean, if you have features in the Bayes optimal predictor, then it is also the right way to make the decision.
I want to stay away from yeah.
Maybe there's different cause to false positive and different cause to positive.
Well, that can fall into the threshold, right?
Yeah.
So I think it's part of this. So I'm gonna try to talk about the false positives and false negatives in a little bit. I would say right is difficult here because what do we ultimately care about? We care about equilibrium effects. Let's think about the criminal justice system, and we want to say 50 years from now, we want to have a more equitable society in some broad sense. It's not clear in some local sense. What is this optimal? To be very precise, what is this optimizing for? It's optimizing for the immediate costs and benefits. If I define the costs as strictly the cost of incarceration, where I'm assuming this is equal across individuals, and the benefits as that sort of immediate effect of someone being assaulted as a result of an individual being released. So this is one sense in which I can talk about.
But to the extent that you've already encapsulated all of those equilibrium effects in saying that you can measure the counterfactual, then I can judge right or wrong relative to that in a pretty objective manner.
No, you can't. If I tell you the counterfactual for one individual, I'm not telling you anything about the equilibrium effects of a policy. So these are very different problems, and I think this is exactly where the tension comes in. So I do believe this is a quite natural place to start, and in fact, this is what people do in practice. But I do want to push back on the idea that this is the only thing that one can do.
there's a counterfactual issue even if you fix everyone's current behavior just because you have sensory feedback, like you don't see what happens for the people that.
But I'm assuming, in the sort of assumption one, I was assuming I have the counterfactual.
I'm saying that there's that, even if you fix everyone's current behavior, there's still this counterfactual question, and now he's saying you deal with that. But that's, I think what Sharad's saying is just the wider scope, which is once you put the policy into effect, then people change their behavior, and then both in the setting where you arrest people, it's like now everything changes, all the correlations are broken potentially.
So I mean, in general, you have the Lucas critique and all of these other types of things. Whenever you intervene on the system, the entire behavior of the system is going to change. And so I think these are very real. This isn't just a hypothetical, but I think it's the main point I want to make here is this is not a crazy policy. Some would argue it's like one of the only reasonable policies. And now I want to show that even this very reasonable policy can lead to all sorts of funniness for classical definitions of fairness. So okay, just a little bit more intuition about what this threshold means. If I pick a threshold, let's say my threshold is 50%. It doesn't have to be 50%, but I'm just going to choose it at 50%. What is this saying? That means on the margin, I would be ambivalent between releasing two people and detaining those two people or releasing them and having one extra crime. And think of this as a real crime, like an assault happening. That's roughly what I'm saying, that I'm happy to release these, or ambivalent between detaining and releasing these two people right at that margin of 50%. And if I have if I really care that there's no assault, and I don't care about incarceration at all, I might move the threshold over here. And if I really don't think that people should be incarcerated, then I might move the threshold over here. So this is an external policy decision, and it's clearly a consequential one. Yes.
So maybe I missed this. You're having a binary variable for violent crime, but your features might actually tell you something about crimes of different levels of severity that might be possible. Are you folding that in, pulling that effect out, or is that something I should think of as some of the features might tell me about the cost?
Yeah, so I think you could do that. For simplicity, I'm just making it binary, but you could fold this all in and you could say, well, really, in practice, you actually typically care about two things. You care about flight risk and violent crime, not even saying exactly what violent crime means, but I have these two things, so I might have to weight these things ahead of time, and now all of this is not binary. It's like some continuous outcome, and so I could do some version of that there. But for simplicity, I'm keeping everything at the binary level. Okay, so now what's an alternative thing that I could do? Instead of just forming this single threshold, is I could have two different thresholds where these depend on the group. So in this picture, there are multiple groups. Think of race groups or gender, any of these other types of groups. I'm not showing you those groups in this population. This is over the entire population, but I could disaggregate that population. Now I have the blue group and the red group, and I might set different thresholds for these different groups. Again, why might I do that? I mean, maybe there's some equilibrium argument for doing that. I think that's a possibility, but it also suffers from this problem that now there's what economists would say is taste-based discrimination in this gap. And what does that mean? That means that I'm detaining per crime that I've prevented, or by detaining people, I'm actually detaining more people than I would need to. And why is that? Because I'm detaining relatively low-risk people in the blue group compared to the red group. So if I were to move to a single threshold, then I could detain fewer people for that same level of public safety. Now again, maybe you want to have multiple thresholds because you have some other objective function that is not about immediate cost and benefits, that is saying something about equilibrium effects. But in the absence of that, I would say the single threshold is quite reasonable by this argument that it's efficient, at least in this narrow sense of the word. Yeah, Alec.
So so you're doing everything in the absence of estimation errors right now. Would there be a reason to think about different thresholds if you have systematically different estimation errors in the different subgroups?
You might. I mean, there might be an exploration argument there for having different thresholds. I think it's definitely possible. Now, what I'm going to argue here is even if everything is perfect, all these kind of common definitions of fairness exhibit bizarre properties. And I don't think that, in the implicit argument, is that when things are imperfect, as of course they always are, these definitions don't magically solve our problem. Okay, So now, that was just a little bit of background. So now I'm going to quickly review these definitions of fairness and try to point out what I view as fairly serious statistical issues with them. So the three definitions that I'll talk about are calibration, classification parity, which is a wide and very popular set of definitions, and anti-classification. So I'll talk about all these in turn, and I want to make three claims. I'll say that calibration does not preclude taste-based discrimination. So this type of sort of inefficiency that I talked about before, I'll say calibration does not preclude that. Classification parity almost always will lead to taste-based discrimination. So this is one of the most popular definitions of equalizing false positive rates, for example. Maybe you've heard of this. Then this will almost always lead to these perverse effects. And anti-classification can lead to taste-based discrimination. I'll define all of these and then discuss these results in turn. Okay, so what does calibration mean? Calibration is a very simple idea that says conditional on risk score. So think of this as your estimated probability. Conditional on risk score, the actual likelihood of recidivism is the same across groups. Okay, so this is going to hold trivially if I don't have any estimation error and my protected group is one of my covariates X, because in the extreme you can just say fit two separate models and everything will work out. But in general, it doesn't have to hold. But this is an example of something that is calibrated. Yeah.
But you phrase it in terms of reoffend, and we are talking about the decision about the bail. So, I mean, you should rephrase it. We are talking about the fairness of the decision of bail. And here you phrase it in terms of reoffend, which is a different...
So this is a very good point. And so there's some slippage. This is the way it's typically defined, in that we're talking about the fairness of decisions ultimately, and I think that is what matters. But the way that people often audit these algorithms is by looking at whether these risk scores are calibrated in this sense. So the algorithm was designed to estimate someone's risk, and we can ask, does it do that job accurately? Once you have that risk, you can do whatever you want, and maybe you're going to draw a threshold, and you can ask at a more social level whether or not you should detain everyone who has an estimated risk of 75%. But the definition, again, this isn't my definition, it's just the one I'm going to put out there that's common, is to see if the score...
What was your assumption?
The what?
Your initial assumption was that the risk scores are calibrated.
No, I actually made a stronger assumption, but now I'm switching and I'm saying, so I made the assumption that you know the true risk score is given X. So now I'm switching and I'm saying, let's look at the empirical definitions and see how they play out. Okay, so let's look at the empirical definition. And so this is real data now. And we can ask, is this score calibrated? And I'm going to show in a minute why calibration doesn't imply that assumption I want, which is why my assumption is stronger. Okay, so here, we have that people who score, this is black and white defendants who score a 7, for example, have about a 60% chance of recidivating. Okay, so now let's see how we can have a discriminatory, I'm going to use this loosely, but I would say many of us would agree this would be a discriminatory rule even if we have calibrated scores.
And we're still sweeping the counterfactual question.
Yeah, so this is a good point. So how does one actually estimate the y-axis? This is tricky. Because we don't, so I'm claiming this is your real likelihood of recidivism. Really what's going on here is that in this data set, people were tracked for 2 years after they were released. And then we could see whether or not they actually recidivated. But if we believe that incarceration is criminogenic, then obviously that's not quite the right counterfactual. So we can't truly estimate this. We have to do something kind of sneaky to get this y-axis, and I'm going to sweep that under the rug. For now, we go into this in more detail in the paper that I'll post at the end. But for right now, I'm just going to sweep this under. Okay, so now I want to give it a very simple example of a rule that is discriminatory, at least informally, but is calibrated. So what do we do? So here's my blue group. Let's say these are my true probabilities of recidivism. So this is probability y equals 1 given x equals little x. And now I want to favor this group. And I know the decision maker is going to draw the threshold right here. So what am I going to do? I'm just going to take my high risk people, my low risk people, and I'm going to pool them together. And I'm going to call them medium risk. And what's going to happen? Well, all of these medium risk people are going to be to the left of my threshold, so none of them will be detained. Okay, so here the point was this is still calibrated. So when I say that somebody is medium risk, in fact, they are medium risk. When I say they're 40% likely to reoffend, in fact, as a group, they're 40% likely to reoffend. But unbeknownst to the decision maker at the end of the day, there were high-risk people and low-risk people there that I didn't tell you about.
I mean, you define your groups according to the feature vectors. Now you are redefining groups, so you're switching context between the introduction and what you're doing here. Because before we said two people are in the same group if they have the same feature vector. So I'm not allowed to do this.
So here, yeah, so you're right, and maybe this is just like a confusion in the presentation, that at the beginning I'm saying, let's put this forward as a positive way of making algorithmic decisions. And now I'm saying, let's look at these definitions. And you're right that that second definition here is violated, or the second assumption is violated, which is precisely the point of this example. So if we only were to look at calibration, what went wrong here, that second assumption is violated. Because now I have these better predictions. The kind of malicious algorithm designer, has these better scores over here that I'm not telling you, the decision maker. And one consequence is that I can discriminate, I can favor this blue group while still satisfying calibration. So what is the upshot here? That we have to use all of our available features, and this again is the content of that second assumption, that we have to use all of our available features when we produce these risk scores, and not doing that can still result in a calibrated rule, and so it looks fair under this definition from the outside, even though we have strategically discriminated against a group. Now this feels like it's a contrived example, which obviously it is, but I would say it's not actually that far from what has happened historically. And here I'll draw the analogy to redlining. It's not a perfect analogy, but I would say it's reasonably close. So here, what is redlining? Redlining is this practice of denying loans to Black and Hispanic borrowers, basically because of their race, but you can't be quite so explicit. And so what do? You just deny credit to certain neighborhoods. And what is the idea here? Well, the bank is strategically removing information and saying credit decisions are only based on neighborhood. And so this looks calibrated. And they can say, well, we're lending to everybody who appears to have a risk of no more than 10%, a default risk of no more than 10%. But what they're not telling us is that they could have relatively easily distinguish between people in that group that were really creditworthy and people who are not really creditworthy. And so it's the same thing of selectively removing information can lead to this type of discrimination while still appearing fair in the sense of calibration. So calibration in and of itself is not, I would say, a super useful way of thinking about the fairness of an algorithm. And even a stronger claim is that basically everything, if we have a sufficiently rich model, is going to produce calibrated scores.
So how do you deal with using things that you're not allowed to use in these contexts now?
Yeah, so I'll talk about that in a minute. Okay. Yeah.
I have a question about redlining specifically. So there's sort of network effects, right? Especially during the housing crisis, those same banks were accused of overlending to minority groups.
Yep.
And one of the problems was the network effect where house prices get pumped up, and then once certain neighborhoods start going under, then everyone starts going under. So how would you address that, especially in the context of defining fairness? Does it even make sense to try to?
Yeah, so I don't know what the answer is. And again, this is going to these like tricky causal inference questions of, should you be lending to individuals or to groups of individuals? And I think this is trickier. All I'm really trying to say by using this housing example is that the idea of strategically removing information like someone's credit history is not crazy, and that's exactly the spirit of this counterexample to calibration that I mentioned. So now I want to switch gears and talk about classification parity. This is arguably the most common way that people audit algorithms. And so this is what ProPublica used when they had this expose on this Bail algorithm. And here, so just to like refresh our memories, what is false positive rate mean? So the idea for false positive rate is first that that we have parity of these things across groups. So the false positive rate for black defendants and white defendants should be the same, or approximately the same. That's the idea. And this is a whole class of definitions, basically anything that can be written down from a confusion table. That's the error metric that we can consider, and then we can ask for parity in that, in that measure. So now, just to refresh your memories here, what does false positive rate mean in this context? It means among people who would not have reoffended if released. This is a tricky counterfactual, but let's just assume we have it. Among people who would not have reoffended if released, what proportion were deemed high risk? Okay. And ProPublica, this is what they found. Again, we redid the analysis, so these numbers are in fact borne out by the data, that the false positive rate for black defendants in this one particular area, Broward County, in Florida, had about a 30% false positive rate versus 15% for white defendants. So among black defendants who did not reoffend, about 30% were deemed high risk by the algorithm versus 15% of white defendants who did not reoffend were deemed high risk by the algorithm. So these are pretty stark disparities, and the I would say explicit statement is that this is strong evidence of bias. And now what I'm going to argue is that it actually doesn't tell us what we might intuitively think the first time. Okay, so again, let's just work through a very simple stylized example. So we have, let's now assume that these are true risk scores. So this is probability y given x. We just have these magically for every individual. We have no estimation error. And we have two different groups. Well, in any two different groups, we're going to have different distributions of risk. That's not saying something that's inherent about that group. It's just saying that the distribution of their covariate vector is different. And so I'm going to have different distributions of risk. So think of this as white defendants and black defendants. But in general, I just have two different groups. And now let's compute the false positive rate for the blue group. How do we do this? Well, what's the definition? Among people who did not reoffend, how many were deemed high risk? We can just count this up. This is only approximate, but we can count this up and say, well, these are the probabilities that they would reoffend. I can just take 1 minus this. I have the probability that they would not reoffend. I can say how many of those people are to the right of this dashed line. Kind of working through this algebra, I get about 25%. Okay? So this is just mechanically what the false positive rate is for that blue group. Now, for the red group, I can do the exact same exercise. The threshold is exactly the same place, but the distribution is shifted. And so what's going to happen here? Well, now my denominator has to be smaller because this group is higher risk on average. The numerator doesn't have to be bigger, but in this case it is bigger, but I just have more of the mass to the right of that line. Okay? And so here I have a 40% false positive rate. So again, applying this single threshold rule, just applying the same standard to everyone independent of their group membership, even assuming these risk scores are perfect, no estimation error, I find this quite large disparity between my two groups. And this is exactly, so this is just kind of, I would argue that this is fair in a sense, and it's hard in practice to think of what one would actually do in this context, other than something approximately like drawing a line and making decisions based on that. And this leads immediately to these big disparities in false positive rates. So this is exactly, so that was just a hypothetical example, but it's very much maps onto what's going on in Broward County. So here, we again don't know the true risk of anybody, but we can approximate it. And what we're seeing here is a heavier tail of risk for black defendants relative to white defendants, which maps onto that stylized example. Okay, so this is what's called in the economics literature the problem of inframarginality. And so the idea here is that this intuitive definition of fairness concerns what happens at the margin. And this definition of false positive rate, or any of these types of things, these summary statistics, are telling us about the entire distribution. And so they're not just telling us about what happens at the margin. We have to integrate over the entire distribution, and now all sorts of funny stuff can happen. So just because I have differences in the tails, as I have here, doesn't tell me that I have differences in the standard being applied. Okay, and let me let me give you sort of a little bit more intuition for what's going on here. So this seems funny and counterintuitive because we're used to working with these types of error metrics. And I would say the context that we're used to working with these types of error metrics is we have one data set in many different models, and we're trying to find the model that minimizes error in some particular sense, so like false positive rates. But here what we're doing is we're flipping it on its head, and we say we have one model in multiple data sets, one data set per group. Now, once we do that, our intuition is breaking down in that whenever the distribution of data in those subsets looks different, the interpretability of error metrics is not the same as in conventional usage. Right? So it's very closely related to what we typically do, but the subtle difference of one model, multiple data sets, versus one data set and multiple models has big implication for interpreting
So
these.
this can be read as some kind of impossibility results, like incomparability of two notions of fairness.
It is, but I'm pushing for an even stronger interpretation. And I'm saying that in a sense, yes, you can't satisfy these things simultaneously. But really what I'm saying is that if we believe that fairness is more closely aligned with the idea of a threshold and these marginal decisions, which I think is representative of the kind of classical literature on this, then this newer idea of thinking about fairness in terms of false positive rates really has fundamental problems. Now, one can push back and say, oh, the problems are in the classical definitions, and really the right definition is in terms of this classification parity. I personally find that a harder argument to make, but one could make that argument. One could try to make that argument. Okay, now let me just push back a little bit more on the intuition here. So here we have these two different groups with two different false positive rates. And we might say, okay, look, this group has a high false positive rate, and we want to lower it. So what can we do? Well, one thing we could do is we can go out and arrest a bunch of college protesters. So this clearly is making this group worse off. But mechanically, what's happening when we compute the false positive rates is all of a sudden, these extra people, these low-risk people that we're going to immediately release, we don't change anybody else's decision, we don't change anybody else's risk, we just take these low-risk people and we put them over here, and now we're going to have our lower false positive rate. So we went from this, which many people, at least using this false positive parity definition, would say this group is being treated unfairly, to this, to be like, oh, now everything is okay, but really we've made this group much worse off. So again, just another illustration about these kind of sort of strange properties of looking at something like aggregate false positive rates as opposed to looking at things like the marginal decision. Okay, so, yeah.
Typically, what people refer to as false positive rate, my understanding is that usually it's if you arrest a lot of people who aren't actually true positives, then you actually have a higher false positive rate.
False positive is the way I defined it. Among the people who would not have been rearrested, who would not have reoffended if released, how many of them are deemed high risk? And so here, what's going on is none of these people were deemed high risk, so none of these people go into the numerator, but most of these people would not have reoffended. They're all low risk people, and so they go into the denominator. So that's the standard definition of false positive. Okay, so again, all of these definitions, you can think about precision, you can think about recall, you can think about all of these different types of parity constraints, and they all suffer from this issue of inframarginality. So now, I think I just have a few minutes left. I was going to talk a little bit about anti-classification, but I'm going to skip this. Here the idea is that in some situations we might actively want to use protected characteristics, and not doing that can lead to unfairness, at least in a colloquial sense. So why is that? Because that protected characteristic might give us real information about an individual's risk. So I'll skip that example, and I just want to at least touch on very quickly bias in the data. I think I have 5 minutes. Yeah. So I want to quickly touch on bias in the data, because so far I've been assuming that that we estimate everything perfectly, and now I want to revisit that assumption. So here I'd say bias in the data, this is a common refrain, and I want to try to, it's very hard to know. We kind of intuitively have a feeling for what this means, but I'm going to try to make that a little bit rigorous, at least on one dimension, of separating between bias labels and bias predictors. So what does bias labels mean? It means that we don't, that y, that left-hand side, or that thing that we're trying to predict, doesn't measure exactly what we care about. So here's an example. So St. George's Hospital in the UK, they developed this algorithm to sort med school applicants. How do you train this? Well, you might train it on past decisions. So we say, well, okay, these are the people, we know all this stuff about them, these are the people we admitted in the past, so we're just going to predict that, and now we can run this going forward. It's not a crazy thing to do. I mean, it's hard to think of things other than this that you're going to do in this application, but it turned out to be an incredibly bad idea. And why is that? Well, past decisions, unsurprisingly, are biased against women and minorities, and so all you're doing is baking in that bias when you fit these types of algorithms. And so the thing that you actually care about, whether or not someone would be a good student, is not the thing that you're training on. You're training on whether or not they were admitted in the past. So there's this measurement error, and that's just what I'm calling a bias label. Another example in our setting, as I alluded to, in reality we measure who's arrested or convicted. We don't measure who would have committed a crime. And for something like street crime, this is pretty problematic because we know that we're just going to observe more street crime where we have greater police deployment. And so then we're just going to have this we're going to pick up exactly what we're looking for. So it's tricky there. Again, the people who are using drugs might not be the same people as are illicit drugs. They're not the same people as people who are arrested for illicit drug use. And again, we're measuring something that's very different than the thing that we actually care about at the end of the day. So now, this is hard. I would say biased labels is arguably one of the biggest problems facing the fair, equitable design of algorithms, is that we have to know what that thing is that we're trying to predict at the end of the day. What are we trying to make decisions based on at the end of the day? And if we can't formulate that coherently, if we can't measure that accurately, it really raises this big question about how do we design any of these types of models, regardless of the functional form. Even if these are simple models or complex models, that functional form of the model doesn't get us out of the problem of whether if that label is biased. Okay, so now just finishing up with the idea of bias predictors, sort of the flip side of this, is saying that using the same example of heavy policing in minority neighborhoods, we might see something like marijuana arrests are biased in the sense that minority individuals who are arrested for marijuana use might be less likely to commit violent acts in the future than white individuals who are arrested for marijuana use. Right? Why is that? Because there might be this over-policing in these minority neighborhoods, and so that means that marginal information that we get from one arrest for a black individual is less than what we're getting for the arrest for a white individual. Now, if that's the case, including in the model and just these kind of simple linear form, is going to mean that we're overstating the risk of minorities and we're underestimating the risk of whites. Now, the simple fix for this, if we believe our labels, is we just fit a more complex model. We fit something with interactions, or we fit separate models, and then we can automatically deal with this. We might learn that one marijuana arrest for someone who is black or Hispanic only increases someone's risk by 5 percentage points, but that same arrest increases someone's risk by 10 percentage points if they're white. So that's a very simple fix, but this kind of points to this idea of why we might need to use that sensitive information in the model itself when determining risk. So here I'll just read this quote from Sandra Mason. She has this paper, Bias In, Bias Out, that makes this point as well. In New Orleans, she's talking about herself. In New Orleans, when I worked there as a public defender, the significance of arrests varied by race. If a black man had 3 arrests in his past, it suggested only that he'd been living in New Orleans. Black men were arrested all the time for trivial things. If a white man had 3 arrests, on the other hand, it suggested he was really bad news. So again, this exact same thing, that the same kind of observed criminal history can mean very different things across different groups, and if one doesn't adjust for that, then it can lead our risk estimates astray and lead to this type of discrimination in our ultimate decisions. Okay, so just wrapping up, what is a kind of punchline here? There are many ways to formalize equity, and we've talked about a few of them, the classification, parity, calibration, and I didn't really talk about anti-classification, but it's this idea that we can't use protected characteristics. And I'd say that many of these definitions, in fact, all these 3 definitions, these class definitions I talked about can't accommodate this very kind of classical, intuitive understanding of equity, for example, equality at the margin. And in my mind, this kind of highlights this danger of trying to formalize equity too much in saying, well, here's my mathematical definition. We're going to look at equal parity, or we're going to look at parity of false positive rates, and now we're just going to design systems with that constraint built in without really interrogating what are the downstream consequences of using that when designing these types of systems. So I think that's one of the first points. And then the second is a much higher level point, in that statistical algorithms are good at estimation and giving us things like risk. But they don't really tell us much about what policy to take. And so in the case of pretrial decisions, instead of detaining individuals, we might, for example, explore non-custodial interventions. And this is exactly what we're trying to do, is that we're active in deploying these types of interventions in the criminal justice system. And so, for example, if someone is deemed to be a high flight risk, maybe that's because they don't have easy access to transport. And so if you were to get them a car to get to court, that might dramatically lower someone's risk. And so thinking about how we can intervene and lower someone's risk, I think is not something the algorithm itself is telling us, but is very important when we're designing these types of systems that have policy implications. So if you're interested, please take a look at these two papers that go over much of what I talked about today in more detail. And if you're more broadly interested in these types of policy interventions that we're rolling out and this kind of intersection of policy, equity, and algorithms, check out some of the work at the Stanford Computational Law School. Thanks.
All right, so we have time for one or two questions, and if the next speaker could come up and.
I think this might have been the part of the talk that you didn't have time for, but a very naive question. The very first algorithm that you showed, where you just give everybody a number for, if you could give a more accurate reading by adding a question, are you black or white, should you add that question?
Are you saying if what I personally say to edit, or you're saying?
Like, in a way, when you use machine learning, you kind of can't take that out, right? Because you can tell if someone's black or white by the correlates.
Exactly. So I think you're right. This is exactly what I kind of skipped over in the talk, is that there's this idea that you can de-bias the algorithm by blinding it. And you're exactly right that you can't do that. And here I was trying to push even further and saying in many cases you don't even want to try to do that. That you get real useful information by including these characteristics that we think of as protected in the algorithm itself. So not just learning it merely by the correlations, but using it explicitly.
So if I understand correctly, you're saying that if your algorithm was the original one that showed in the papers, you would add that, right?
So I think, so we haven't found empirical evidence that adding race improves the quality of these types of algorithms, but there is a lot of empirical evidence, both from our group and from other people, that gender is super informative. And so if the same criminal history, women tend to reoffend less than men. And so Wisconsin is one example. The state of Wisconsin is using gender-specific risk tools. This actually went up all the way to the Wisconsin State Supreme Court, and the court deemed that this was an acceptable use of gender, of this protected characteristic in the model. I think it's pretty complicated. I mean, the flip side.
I just want to add a comment on this, because it's really a question of why do you not ask someone about their race? Because you're afraid that who makes the decision is a human that is biased. It's a different model when the decision is being made by an objective algorithm that's trying to optimize some utility. So there are two different scenarios here. Do we want to protect against humans that may have a bias when they're making a decision, or do we want to optimize some algorithm? And in that case, asking about race is completely legitimate.
Yeah, but the algorithm is learning from past data where humans were biased.
Yeah, that's the dynamics of time. It's a different story.
Sure.
I think I am. Can I answer one more question, Matthias?
Yeah,
or am I? Okay.
Sure, just one quick question. When you talk about race, did you take into account the particular normalized data for the race? For instance, average income or median or whatever, and then normalize for the races. Let's say. Because we talk about median income and somebody's over and below, but then relative to the median income for the particular race, then things change.
Maybe so. Is the idea that you're trying to de-bias the other information? Yeah. So this is related to this question over here. That one kind of popular approach is we really want to take the orthogonal projection. We want to get rid of race and say, now, well, you told me about income, but if you tell me about income, that's really telling me about race, and so let's try to get rid of some of that information. And the argument is, unfortunately, I kind of apologize that I couldn't get to the examples, but the argument that I'm making at a high level is that in some cases you explicitly want to use that race information.
You want it, yeah.
And this is counterintuitive to many people. The kind of the default is a lot of how these papers open is, well, by law, we can't use these characteristics. And in fact, you can if there's a good reason. And this is the example of gender that we can use. In that case, at least Wisconsin deemed that we could use it. So I'm gonna get pulled off, but
fairness to the next speaker.
yes, I'm happy to please harass me outside and on the panel.
Don't harass him.
Don't harass me.
Please.
Please ask me questions.
Yeah, there we